MATLAB functions as a powerful digital laboratory, a place where we can accurately render physics from raw numerical data. To build a simulation, we rely on a specific foundational toolkit: arrays to organize the data, loops to control execution, and error analysis to maintain accuracy. We solve engineering problems by combining these tools. A single loop handles repetition, but linking that loop to an array of equations allows us to model a system's behavior over time. We will demonstrate this by modeling two systems: the trajectory of a cricket ball hit for a 6 and the steady-state heat transfer through a metal rod. Moving from a physical observation to a functioning script requires a specific logical structure. This process begins with the organization of the workspace. Before writing any equations, we must define the architecture of our script. Maintaining a clean workspace prevents variable conflicts and keeps the logic transparent. Professional scripts use 3 mandatory blocks. The input block holds your parameters. The computation block contains the solvers. The output block displays the results. This modular approach isolates the physics from the display logic. If the code fails, you can verify your parameters in the input block without digging through the solver's internal math. We can simplify the input block by using a structure variable, like param. Instead of passing 10 individual constants, we pack them into param.g for gravity or param.k for drag. This allows us to hand a single, organized package to our solvers. Disciplined code structure ensures that as your model grows in complexity, the script remains readable and easy to update. Our first task is modeling the trajectory of a ball hit by MS Dhoni. We define our physical parameters in the input block: gravity at 9.81, an air drag coefficient of 0.006, and a launch velocity of 35 meters per second at a 45-degree angle. Since we know the exact state of the ball at the moment of impact, at time 0, we are solving an initial value problem, or IVP. To solve an IVP, we move to the computation block and use the ODE45 solver. This function takes our starting position and launch velocity and computes the trajectory forward through time. Finally, we use the output block to plot the coordinates. We can see immediately if the ball's path clears the 75-meter boundary line. When you possess a precise starting point and the governing equations of motion, you can predict how the system will evolve. Other systems aren't defined by a starting time, but by fixed conditions at their physical edges. Consider a metal rod held at 100 degrees Celsius on the left and 25 degrees on the right. In this scenario, we need to find the temperature at every point in the middle as heat escapes to the environment. This behavior is governed by a second-order differential equation. It describes the relationship between the temperature at any point x and the surrounding ambient air. Because we are solving for positions between two fixed points, OD45 is the wrong tool. This is a boundary value problem, which requires solvers like BVP5C. We can also use the finite difference approach. By discretizing the rod into 10 intervals, we calculate the temperature at each node. MATLAB's default math is linear algebra, which treats variables as whole matrices. However, we need to perform operations, like squaring values, on each node of our temperature vector individually. To bypass matrix multiplication logic, we use element-by-element operators, dot-caret and dot-slash. This discretization creates a tri-diagonal matrix system. We then apply the Thomas algorithm to solve the temperature across all nodes simultaneously. The output plot shows the result: a smooth curve illustrating the temperature drop across the length of the rod. Solving these problems requires recognizing that the system is defined by spatial constraints rather than a chronological sequence. By applying these techniques, we have successfully modeled 2 distinct physical systems. The side-by-side plots demonstrate the utility of the 3-block structure. Whether we are tracking a moving ball or a stationary rod, the input block stays organized and the output block stays clear. The key to modeling is identifying the information you have. If you have data at time 0, you use an IVP solver. If you have data at the physical edges, you use a BVP approach. Mastering arrays, structures, and specialized solvers gives you the tools to convert physical observations into functioning numerical logic.